Hello everyone. In this short video, I'm going to give a very brief introduction to genetic algorithm. I hope you can get a general idea of this algorithm and be able to implement the simplest form of this algorithm by watching this video. First of all, whenever you are thinking about an algorithm, the first thing you should think about is not the algorithm itself. Instead, you should think about what problems people want to solve with this algorithm, and then why it can solve this problem, or hopefully why it can solve this problem better than other methods. From this angle, you are more likely to capture the essence of this algorithm. For genetic algorithm, it is designed to solve the search or optimization problems. In a sense, these two kinds of problems are equivalent to each other. You can consider an optimization problem as a search of the feasible set of optimization. On the other hand, you can also consider a search as a process of trying to optimize the quality of your solution. For conciseness, let's use an optimization problem as an example. In this example, we want to maximize sine 7 times x and plus x such that x is between 0 and 5. In fact, before the genetic algorithm was created, there had already been many numerical optimization methods. So why do we need genetic algorithm? To answer this question, let's first try to solve this problem by the traditional methods. For a numerical optimization methods, we need to set the initial value of our design variables. Here, x is our design variable. And then we improve the value of the objective function iteration by iteration. Suppose that we set x to 1, and a traditional method will give us a solution of x equal to 0.75, and the objective value at 0.75 is around 2. But we can see from the graph that this solution is not good. So let's try to set x equal to 2, which will give us an objective value of roughly 6, which is better, but still not optimal. Let's try another one. Let's set x to 3, and we can get 8 as the objective value, better than all the previous ones. But to get the optimal one, maybe we need to set the initial x to 4. Then we get the best one, which is roughly 9. But any problem with this method? Yes, we have tried 4 initial values, and this problem only has x between 0 and 5. What if x is between 0 and 1,000, or even negative 10,000 to positive 10,000? How many initial values do I have to try? Okay, now this is where the genetic algorithm comes in. It just doesn't require you to try initial values one by one. Generally speaking, genetic algorithm is inspired by the biological evolution. Taking an animal as an example, do you think it is only because these animals are lucky that they can survive in this world, being what they are now? No, apparently not. It's because the evolution. Evolution is just a magic optimization process. It optimizes the animal's ability to survive in this world. And the genetic algorithm is just trying to simulate this process to solve the optimization. Let's give it a very quick look at the flowchart of the genetic algorithm, and I will talk about each step in details later. First, you need to generate an initial population, and then you calculate the fitness value of each individual in this population, and I will tell you later what is the fitness value is. After that, you need to decide whether you want to terminate this iteration or you go on to the next step. In next step, you need to select some individuals from your population and let them reproduce or copy them. After that, you need to do an operation called crossover, which basically exchange the information, the genetic information between these individuals in your population. After that, mutation is going to happen in your population according to some very small mutation rate. After all this operation, you will get a new generation, and you take this new generation to the second step and do all the operations again and again. So we can say that genetic algorithm is an random search algorithm or a global optimization algorithm. In the first step, we need to generate an initial population. A population here is actually a set of candidate solutions. For example, all the real values between 0 and 5 can be a candidate for our example problem. Then, how do we represent a solution in our algorithm? Actually, we represent it by some codes. When talking about codes, we need to define at least two functions for that. One is encoding, the other is decoding. The way to encode or decode varies a lot in different problems. For example, we can use, just as in the table, encode real values by characters. For example, we can encode 0.1234 to A, B, C, D, E, and in the same way, we can decode E, A, B, C, D to 4.0123. But you might know that in computer, numbers are in binary codes. So in our problem, we use the binary codes for implementation. You can also refer to a table here to do the encoding and decoding of binary codes. I should say that why we need codes here. Because we are trying to simulate the biological evolution in which each individual is encoded as a DNA sequence. So all the improvement from generation to generation are reflected in their DNA sequence from the evolutional angle. In the next step, we need to calculate the fitness value of each individual. So we need a fitness function. A fitness function is a function you use to evaluate how good each individual is. The better an individual is, the more likely it can survive in this environment. For solving an optimization problems, we can use the objective function as a fitness function. Or You can define any other functions which are equivalent to the objective of your problems you are trying to solve. Now, we have a population and the fitness values of each individual in this population. And we have to make a decision about which individual is going to survive and which one is going to be removed from the population. And the vacancies of the removed individuals will be occupied by the copies of the remaining ones. So we can do this decision randomly by converting the fitness values into a probability distribution, and then sample according to this distribution. For example, suppose that we have 3 individuals here, and they have the fitness values 3, 5, and 9 respectively. So they will have the corresponding probabilities that they will be selected and be copied into the next generation, and these probabilities are listed in the second row of this table. So as you can see, in this way, the better the fitness value is, the more likely this individual is going to be selected. And then the reason why I do this copy operation is we have to maintain a constant size of the population. So unfortunately, for the ones that have not been selected, we have to erase them from the population. When animals evolve from generation to generation, they will exchange their genetic informations within the population. Note that in this process, both better or worse individuals can be generated compared to the parent generation. So we have to limit this operation to preserve the currently best individuals. Here's how we do it in our example problem. For example, we are going to do a crossover between these 2 individuals coded as these 2 binary sequence, and we will just use some snippets of the sequence from the first individual and combine these snippets with some snippets of sequence, the coded sequence from the second individual. Now we combine these 2 individuals into a newly generated individual. This is how we do the crossover operation. Along the long trajectory of evolution, crossover of only existing genes are obviously not enough for animals to be what they are now. New genes have to be created. This is mutation. The individual with mutated genes will show features that has never been shown before. For example, we can simply flip a snippet of code of an individual, but just as what we did in this table, but we need to be very careful when we do this to make sure that all the mutated individuals are still valid ones according to the problems we are trying to solve. For example, we expect that all the mutated individuals still represents a a valid value between 0 and 5. You don't want to create some monsters in this step, do you? Also, as crossover, you don't know what you are going to create by mutation. You may want to limit the mutation to only a very small portion of the population. Okay, finally we covered all the steps in the flowchart. And just let me stress the most important things again, because we need to get the idea of why this algorithm works. Basically, it's because these three steps listed here: selection, crossover, and mutation. Because these steps are going to help us explore more and more solutions, and at the same time preserve the best ones for us. So you have known the basics of genetic algorithm. Then we return to the optimization problems at the beginning of this video. How does it look if we use the genetic algorithm on this optimization? Okay, here it is. As you can see, instead of only manipulating a single red dot, we have a set of red dots now, which is our population. As time goes by, these individuals will gradually gather around the maximum value of this curve. Now, you don't need to worry about the initial values of design variables. Just let the algorithm explore the world for you. And in the AI field, there are also many other algorithms which are similar to genetic algorithm and also simulating some natural processes such as ant colony, artificial immune, and particle swarm. Okay, that's all I want to talk about in this short video, and thanks for your attention. Bye bye.